My name is Fred Kim. I work for HBM nCode as an application engineer. I'm based in France, as I'm sure you have guessed from my accent. This webinar is about science sweep on random. Well, if you look at the title, it's long and complicated, but it could probably be replaced by how to reproduce engine vibrations on a shaker table. Please note there's a picture of an automotive engine here, but just keep in mind that this will apply to any rotating machinery in general, like turbine or gearboxes, etc. So this presentation is based on a work and a paper made by Benoît Baume, who's an engine vibration expert at PSA Peugeot Citroën in France, and myself. It was presented at TIG Design in Setim in France end of last year. And the original paper can be downloaded from our internet sites. So let's start with an introduction to the vibration qualification tests, to the accelerating testing methodology, also known as test tailoring methodology, and how it can be applied to the very specific case of rotating machinery vibrations. Yes, just first, allow me just to introduce HBM nCode very quickly, just the three products the three software we're developing at nCode. I'm sorry, just to help maybe position which one we are talking about here. So we're part of HBM, and the nCode part of HBM is taking care of developing three softwares. We've got GlyphWorks here for data processing, and this presentation belongs to this area here. We're talking about signals and vibrations and data collection. Right? We've got Design Life for fatigue simulation on finite element models. And we've got automation, which is, if you like, an engineering database, where we've got also data processing enabled, such that you can do very synthetic reports like this one. So now we're talking about qualification tests, durability tests, vibration tests. What do we want from such a test? Basically, such a test must replicate the same failure mechanisms as the ones seen in the real world. Also, the test should be representative of the real loading environment, and the test should, if possible, should be accelerated to reduce project timescales and costs. So, in order to meet these conditions, two steps are generally required and identified. The first one here, called mission profiling, is the most important one. It's the base of all. It's also the most difficult and time-consuming. It's about capturing the real-life loads and assessing the product's real usage. Long-term monitoring is often required to do so, and that's where a software like automation is ideal for this exercise, because it contains a database of signals and is able to run analysis like tendencies across a whole project. Now, step 2, test synthesis, involves finding a damage equivalent test specification. Here we try to synthesize the whole mission profile, accelerate it while staying close to the nature of the input load in order to be still representative of the real loading environment. Right? Well, the objective of mission profiling is to identify typical events with their number of repeats, variability, so typical events of the life profile. As an aside, note that in GlyphWorks we have a module called Optimized Testing that can help you doing this exercise of turning a whole mission profile into a number of repeats of individual events, but that's another subject. So eventually, a limited number of situations are identified and can be reproduced on test tracks, for instance, in the automotive world, or on hydraulic test rigs. But for components, we want to reduce it even further by doing a vibration test on a shaker. Right? For an engine-mounted component like an EGR valve or turbocharger, filters, pumps, electronics, ECUs, etc. Here the mission profile is often represented as an engine speed usage profile. This is basically an histogram showing how long the engine will spend at various speeds in its supposed life. The test tailoring approach, also known as the accelerated testing methodology, consists in transforming all sorts of inputs here, PSD, sine sweeps, time series, etc., into a fatigue damage spectrum. So we go from measured data into the fatigue domain using what we could call a fatigue transform, if you like. Then the synthesized and hopefully most of the time accelerated equivalent PSD here is obtained by doing the inverse transform. This means, in other words, that the synthesized test spec will have the same damage content as the original input signal. Details about the accelerated testing approach are given in papers by Andrew Halfpenny, and you can find them on our website again. Huh? So the test tailoring approach enables to synthesize, accelerate a whole mission profile into a single equivalent PSD, for instance. So having said all this, there are a few challenges now. We must extend the test tailoring methodology to accept engine vibrations, which are often represented, as we'll see, as sine sweep on random processes. Right? Yes, indeed, engine vibrations are complex in nature. They're actually made of engine harmonics on the top of random vibration. This is a complex and composite environment. So the way to address this is to separate dominant harmonics from noise, which is order extraction. Find a way to go into the fatigue domain, so a way to calculate the fatigue damage spectrum from a sine on random signal, and eventually create an accelerated sine sweep on random test specification. So first task is to identify dominant orders, which are harmonic in nature and are therefore similar to sine sweeps. Right? We will extract these orders and subtract them from the rest of the signal. This will give the random part of the sine on random. Various order extraction techniques exist, and we'll have a look at 3 of them. First, what is an order and what is order analysis? Well, rotating machines generate vibrations due to detonations in cylinders, balancing issues, or misalignments of rotating axes. And vibration may vary proportionally with the speed of the main shaft. They do vary proportionally with it. And multiples of the fundamental speed are called harmonics or order. So order tracking objective is to identify the various orders that are effectively buried into the signal and extract their characteristics. So for instance, here we've got an engine run-up, a signal from an engine run-up made of an analog vibration signal and the speed in RPM, speed of the main shaft. On the right-hand side are the results of an order analysis. Typically, we've got order slices or amplitude spectra of the most dominant harmonics And possibly we can get waveforms in the time domain of these spectra, right, of these orders. And the waveform extraction is important in our case because it can be subtracted from the original whole signal. The first and most popular method for order analysis and extraction is the classical FFT-based waterfall analysis. It performs sliding FFTs on time domain data. The user selects mean RPM, max, and delta RPM, mean, max, and delta, right? Plus the usual FFT parameters like buffer sizes, windows, etc. And the instants in the signal corresponding to the various RPM values are found. Now, FFTs are performed, and in each FFT, are done in every RPM band. Keep in mind that the underlying assumption in this type of analysis is that there is very small frequency change within a single time block, so that the assumption of stationarity necessary for the Fourier transform can be considered as valid. Now, if the frequency of a periodic component changes with time, within the time block, the FFT will produce an error called smearing. The energy is distributed in that case rather than concentrated. The peak value is different from the real value at the frequency of interest. And that's where the uncertainty principle comes. There's a trade-off between frequency resolution and speed resolution. For instance, a larger buffer of data points will give a good frequency resolution, whereas a shorter buffer better accounts for speed changes. Ideally, it would be useful to have a large buffer size for low speeds and a rather shorter buffer size for high speed. So, waterfall-based analysis is a very common approach. It's easy to use, and it's ideal for a quick overview for troubleshooting. However, it's very low in terms of accuracy, and it produces no other waveform, only spectra. So let's have a look at another technique, considered this time as the most accurate one. It's called the revolution-based resampling technique. Here, time series are sampled at constant angular intervals. So the input signal is no longer versus time, but versus number of revolution of the main shafts. In this type of resampling analysis, it's recommended to resample at a power of 2 points per revolution, such that the FTT algorithm, which will always pick an integer number of revolutions. Here, each block represents an integer number of revolutions. We can therefore consider that the data contained in each buffer is periodic, and there is therefore no leakage. Doing an FFT of data sample in the revolution domain also solves the problem of frequency smearing, because it is equivalent to performing the FFT over a shorter time as the RPM increases. Right, in this, for instance, here, the transform, the resampling takes this rapid change in speed into consideration. So the revolution-based resampling technique offers a leakage-free order slice plots with a very good accuracy. And the waveform, as shown here, the waveform of a specific order can be obtained by simply bandpass filtering the resampled signal around the desired order, and then by resampling it back into time domain. So we should have all what we wanted, right? The very good accuracy spectra plus time signals of every order we are looking for. But computationally speaking, this approach is very intensive, or can be very intensive, very slow, because of the amount of data that you want to resample at very high separate sometimes. Now there is a third method, which should answer both needs of accuracy and processing speed. It's using an order tracking filter. And this order tracking filter is new in version 8 of GlyphWorks. So it's an adaptive bandpass recursive filter, which is centered at a frequency controlled by the RPM channel. See, that's the filter shape, if you like, and its center frequency depends on the RPM channel. Filter bandwidth can be constant frequency or constant order. It's up to the user to choose. And the number of poles, or the filter order, if you like, controls the selectivity of the filter. And the output is a new signal, which is bandpass filtered around a particular order. So that's the waveform of an order. So this order tracking filter is able to extract the waveform of an order, and the spectrum is obtained by calculating the FFT of the time signal, right? The order time signal. Results are as accurate as with the revolution-based approach, and the processing time is extremely limited. It's very fast. Typically, for an analog signal of 1 million data points, it takes 1 second to filter. So it's very fast. The order tracking filter is the solution we want to retain here in this type of application, because it gives all the necessary information about orders, and it is accurate and it is fast. Back to the agenda. Now we can see how to go into the fatigue domain when our signal is made of a mixture of swept signs on random, because we have swept sign, which is the order we've just extracted, and we've got the leftover, or the remaining signal, if you like, which can be considered random. So we can build a swept sign on random profile from order extraction. Let's see how we get the FDS of it. The first thing to say about sign on random is that it has a composite nature. It is made of the sum of a deterministic, which is the sign, and a stochastic or random process. And that's the sign on random, an example signal of sign on random. And it's always good to remember that the damage of a sign on random process is not the sum of the individual damages. And this is simply because damage and stress amplitudes are not linearly related. It's a power law, and actually doing the sum of damage due to sign alone and the random alone will not be equal to sign random. The damage of sign random is typically much higher. So let's see how the FDS of a fixed sign random process is obtained. By fixed, I mean the sign is not moving, is not swept. It's constant frequency. Damage from a random PSD is typically based on the statistical moments of the PSD as described by Rice back in the 40s. And the idea here is to sum statistical moments coming from the PSD with statistical moments coming from an equivalent narrow bandwidth process to the sign, right? It's equivalent after going through a single degree of freedom system. Once we have the sum of the moments, the damage is calculated as usual using the right formulation to derive the distribution of peaks and of the process. Again, there are papers by my colleague Dr. Andrew Halfpenny, which are available on our website, and these papers give far more details about moments and random fatigue analysis. Now, I haven't introduced the ERS, but that's another spectrum we may want to calculate, and we'll see later why. ERS stands for Extreme Response Spectrum. The Extreme Response Spectrum represents a plot of maximum likely acceleration amplitude to occur with respect to the natural frequency of a one degree of freedom system. It's very similar to the well-known SRS. And calculating the ERS of a Sine random is much simpler. It's actually the sum of individual ERS of the Sine and the PSD ERS, right? Note that this is only possible under an assumption that the number of cycles is higher than 10,000. And this is not a very restrictive condition because it happens in most of the cases. So now, what if the sign on the top of random is swept, as it's the case for run-ups and run-downs, right? Well, the fatigue damage spectrum for such a swept sign on random loading is obtained by dividing the test into a number of discrete sign on random tests. And all those sign on random would cover the whole frequency range that are swept. And then we'd sum all individual FDSs to create the final swept sign on random FDS. The duration associated with each sign on random segment depends on the sweep type chosen, like linear, logarithmic, and the total test duration. And by summing those individual fixed sign on random FDSs, we eventually get the FDS of a swept sign on random load. Same for the ERS. So in practice now, say you have a measurement coming from a run-up test. First thing to do is order tracking filter, right, to separate the dominant orders from the rest of the signal. The orders will become swept signs. The rest of the signal here, if stationary, can be considered random and therefore be turned into a PSD. So here we've got a swept sign on random, and the FDS can be calculated using the algorithm that we just described. Note that the engine usage profile can be used to scale the duration at various RPM, because we know that the engine will spend that many hours at that RPM range. So we can use this one to scale up the FDS for different frequencies. Some applications of the FDS. One great application in general of fatigue damage spectrum is to compare severities between specifications. So from all sorts of input signal, we can derive a fatigue damage spectrum, and we can compare them. There's a white paper called Synthesis of an Engine Vibration Spec and Comparison with the Existing Qualification Specification that is available from our website. It's been written by David Dolo, who's a vibration specialist at Valeo, and myself. Some added value applications of fatigue damage spectrum include running a limited number of tests. For instance, if the swept sign on random covers in terms of damage other required qualification test profiles, well, why not simply running the swept sign on random? We can also do a sorting of various situations of a live profile based on severity, or if you like, it's assessing the damage contribution of every situation of a live profile. We can also use this one to convert between, for instance, sine sweep and random. If they've got the same, if a given sine sweep and a given random profile, but the associated duration and properties have the same fatigue damage spectrum, then they are equivalent in terms of damage across the whole frequency range shown by the spectrum. And another application is simply to use the fact that damage can be summed using the minus rule, and such that the damage from various situations in the life profile can be summed linearly, and eventually, once we've got a global FDS, we can find an equivalent PSD. And by saying this, I've summarized the whole test tailoring or accelerated testing approach, right? So it's very, very important to be able to turn our swept sine on random into the fatigue damage domain and looking therefore at the fatigue damage spectrum. So now, how do we obtain an accelerated swept sine on random test specification with a given sweep rate in octave per minute, for instance, but with the same damage content as the fatigue damage spectrum calculated using the engine usage profile file? Let's have a look. The objective here is to incorporate the engine usage profile into the characteristic of the swept sine on random that we want to obtain. This swept sine on random has a given sweep rate, right, which should replace the engine usage profile. So it should have the same damage content as the measure. So there are basically two ways of doing this. One can iterate manually until the both FDSs match. That's a sensible way of doing it, especially if you have an idea a priori of the spectrum you wanna apply. Or you may want to run the test tailoring approach separately on sine sweep and on random, as I'll describe in the next slide. Right here are more details on treating separately sine sweep and random. The sine sweep is treated in the time domain. Extraction of sections in signal are made that they correspond to the various RPM levels, and the engine usage profile file is also used to in this box here to multiply the FDS accordingly, and eventually we find a swept sine that's equivalent in terms of damage, and this swept sine can be accelerated, and it's got a given sweep rate, number of repeats, etc. Same thing with the leftover signal or the random part. If you want, we can apply the test tailoring approach, scale the FDS with the ISIP file, and obtain an accelerated PSD. And swept sine plus PSD gives the accelerated swept sine on random profile. Right, some examples. I'm about to show an example made at PSA, Peugeot Citroën. Measurements were made on a 4-cylinder diesel engine. So the vibration were measured on cylinder head during engine run-up with engine at full load. Only the vertical axis of the engine is considered here. It's the piston axis, right? The first step, as we saw before, is order extraction. H2 and H4, or second and fourth order, are dominant, as it's 4-cylinder engines. They are extracted using the order tracking filter, and here we can see their waveforms. Note that the same extraction was made using a frequency-based approach. It gives extremely similar results. For instance, you can look at the blue and red spectra here. They overlay almost perfectly. So that gives us good confidence in any approach in the end that we can use. But we prefer order tracking filter because we get the time domain waveform. Now we have the sine sweep, and the random coming from these order extraction. Sine sweep is coming from the orders of the engine, and the PSD is coming from the rest of the signal, right? We can compute the FDS and ERS as described previously. And here again, we decided to compare the stochastic approach, frequency domain, right, with the time domain approach here. And the results are extremely close. This enabled us to validate our spectral approach. Note that the time domain route is far more time consuming, and it does not have the statistical content that the frequency-based method offers, because the spectra obtained after the spectral method are indeed smoother if you look at the red one, because they're not coming from one single signal, but they're rather obtained using statistical distributions and so on. So we prefer working in the spectral domain. So now that the method of calculating FDS directly from the swept sine on random using a spectral approach, now that this method is validated, let's do it properly using the engine usage profile file. Note that this EZIP file lasts for 7,500 hours. And the objective is to find a swept sine on random profile to run with a given number of sweeps and given sweep rate, but total test duration is 100 hours. So we want to reduce the test duration by a factor of 75. What was done here is as described earlier. The accelerated testing or test tailoring methodology was applied separately to the sine sweep and the random process. And the EZIP file, the engine usage profile file, was included. The obtained sine sweep and PSD are displayed here. The blue corresponds to a duration of 7,500 hours, and the red are for duration of 100 hours only. So we may consider the red spectra to be our swept sine on random test specification. Now, a legitimate question could arise. Are these high levels still realistic? Are they still representative of the real environment loads? And in other words, if you prefer, have we accelerated this test too much? Well, that's where the ERS is involved. The ERS allows comparing maximum responses to check if the reduction of the test duration was not too drastic. We used here our spectral algorithm to work out the FDS and ERS of the obtained swept sine on random in the case of 7,500 and 100 hours, right? So that in red, you can find the ERS of the accelerated test spec, and in blue, the one for the long duration, the original duration. So ideally, we want the maximum response on the shaker to not exceed the maximum response over the real duration by a factor of 2. And this rate of maximum responses is called the exaggeration factor. And here we can see a plot of the exaggeration factor, and it's below 2, which is a typical threshold that we apply. And below 2 means it's not being accelerated too much. It's acceptable. So this is the final test spec. The qualification test will last for 100 hours. And you'll note that the profiles have been simplified a bit by defining a limited number of breakpoints in this case. And note that the FDS was calculated again to make sure this simplification still has the same damage contents over the range of natural frequencies of interest. Right, I will show you a very quick demonstration in BeliefWorks of most of what we just covered. So this is GlyphWorks. It's made for the ones who don't know of glyphs that you can pick up from a palette of glyphs here. So we've got different areas, different places where glyphs could be found, right, according to different applications. And here we've got the glyphs for accelerated testing. Here for frequency, order extraction, etc. So a first construction, first macro, first flow, as we call it in GlyphWorks, that I built for you is showing signal generation, analysis, and display. In generation, we can create spectra like this one here. That's a random spectrum, a PSD, and it's defined in the table by entering the breakpoints. Note that we could have defined, instead of a random PSD, we could have defined a sine sweep, sine dwell, sine on random, etc. There's another generator that creates time series, and this one as well can generate a sine sweep and simple sine and squares and sine on random, all sorts of signals. And here, for instance, I decided to create a random signal which has the same PSD as this profile. And I decided to run a fatigue damage spectrum from this PSD over a range of frequencies, which in this fatigue damage spectrum is displayed here. And I did the same in the time domain to eventually compare fatigue damage spectra. And actually, I will overlay them both, right? That's an interesting plot. Here, what we can see is that the spectral approach is smoother, and it doesn't depend on one single sample of signal, right? It's using statistical distributions to compute damage. So we tend to believe that this is more appropriate for long-term vibrations, and it's also much quicker. So that was a general presentation of what we can do in GlyphWorks in terms of signal generation and analysis. We mentioned order extraction. So now the input signals, for instance, are an RPM signal and a vibration signal in acceleration, right, coming from a run-up test. We do a waterfall analysis to look at the waterfall plots, Campbell diagram, and here we see beautiful orders popping up from this spectrogram. We can ask for the order to be displayed underneath. So, for instance, let's display order 4. The order value is displayed on the top left-hand side of the. I hope you can see this little yellow post-it. Then order 6, for instance, right, and order 2, which is the predominant one. Order 2 is here, right. So we can overlay those orders, and here we see that the second order covers everything. So that's fine. That's the FFT-based order extraction. But let's have a look at this new order tracking filter. This one enables the extraction of the order waveform, so we get a signal in seconds. And by zooming, we see indeed that it looks like a sine, and actually it's a swept sine because frequencies become very high at the end when RPM goes high. And in there, we've got a set of parameters enabling us to define what's the order value we want to choose, we want to extract, and the order of the filter, number of poles, if you like. And we can do either band pass or band stop. So here, I decided to extract the second order, but I could have chosen band stop. And in that case, the entire original signal would be output without the second order. So that's a way to get either the waveform of the order or the waveform of the leftover signal, the random part. And finally, an interesting one is we compare here fatigue damage spectrum from a random profile. You can see it in blue. That's a random profile. Then we've defined also in green sine sweep. So that's the fatigue damage spectrum of the sine sweep. And in red, it's the fatigue damage spectrum of the swept sine on random. So how did I do that? Here, random noise with the table of breakpoints. Here I've defined the swept sine. So there are two sines that are swept from 20 to 40 Hertz with an amplitude of 3 Gs, and from 40 to 80 with an amplitude of 2 Gs. And here I've defined random and swept sines defined this way. This is a prototype yet. And I'm asking the fatigue damage spectrum and extreme response spectrum for all three processes. And what we can see is, indeed, the red one is not the sum of the blue and the green, because look at the scale is logarithmic. So this is far more than this value here, right? Also, what we can see is outside the frequency range of the sine sweep, it goes from 20 up to 18 total, right? The damage, if only the sine sweep is considered, right, is dropping drastically, whereas sine on random converges to the damage of the random purely random. Same at very low frequencies where damage is typically very important, right? So that illustrates the why obtaining fatigue damage spectrum of sine on random can be very important, very interesting to look at. Well, coming back to the presentation, the only remaining thing is the conclusion. So what we did is first an order tracking analysis to build a swept sine on random test specification. Secondly, an algorithm to calculate the FDS and ERS of a swept sine on random was created. That enables to go into the fatigue domain. And thirdly, there was the development of a new specific test tailoring methodology to obtain an accelerated swept sine on random test spec, which contains the engine usage profile, and which is probably the best synthetic representation of an engine regression environment.